Okay, this is a question from your assignment 8, part 2, question 2, and it talks about the power coefficient, gearbox efficiency, and generator efficiency for a horizontal axis wind turbine. I just want to clarify what all those things are. So if we have, let's make boxes for each of these components. So we'll have the turbine. So that's the actual blades and how well those blades are able to transfer the energy in the wind to the mechanical energy of the blade. And then you have a gearbox that gears the rotational rate of the blades to the rotational rate that you need in your generator. And then you have your actual generator that is generating the electricity. Okay, so the wind, the power in the wind is your input. Then that turns into power in the shaft of the turbine, which turns, we'll call this power of the gearbox, coming out of the gearbox. And then out of the generator is coming the electrical power. And each of these processes has an efficiency associated with it. So for the turbine, that's called the power coefficient. That's the CP. And that would be the ratio of the shaft power to the wind power. And that's the one that's associated with the Betz limit. So the theoretical maximum of that is the 0.59. Then we're going to call the gearbox efficiency eta GB for gearbox. And that would be the power in the gearbox divided by the power in the shaft. And then we'll have an efficiency for the generator, call that gen, and that's the electrical power over the gearbox power. Now, depending on how big the machine is, these values have different ranges. For large machines, this power coefficient is only as high as 0.5. The gearbox is pretty efficient. It can be anywhere from 0.8 to 0.95. And generators are phenomenally efficient as well, from 0.8 to 0.95. Okay, so the overall efficiency, we'll call it eta total, is just the product of these three efficiencies: power coefficient, gearbox coefficient, and generator coefficient. Okay, and we were given all these numbers in this problem. So the power coefficient was 0.42, the gearbox 0.83, and then the generator 0.91. So those are typical values for a fairly large machine. And so the overall efficiency for this turbine, when you multiply those three together, becomes 0.317. So about 32% of the power in the wind actually goes into electricity. But that's okay, the power in the wind is free. Okay, now the next thing you'll notice is it tells you that this turbine operates in Nevada. So we have to calculate the density of air in Nevada. So the density of air is given by the linearized formula, 1.225 minus 1.194 times 10 to the negative 4 times z, where z is the elevation. So we put 1300 in there, 1300 meters for Reno, Nevada, and we come up with a density of air of 1.070, as we expect, less dense at higher elevations, and that is kilograms per cubic meter. Okay, and the power in the wind is directly proportional to that density. Okay, so now all we have to do is calculate the electrical power. So P, the final stage of the process, P electric, would be the total efficiency times the power, P0, power in the wind. Well, I can call it just power in the wind if you like. Okay, so that's eta total times 1/2 rho A U0 cubed, where A is the area swept by the rotors. U0 is the speed of the wind. So A would be pi r squared. So it's pi times radius, not diameter. We're given the diameter, so you have to use the radius, 20 meters squared. U0 is 17 meters per second. And putting all that together, it would be the 0.317 times 1.070 kilograms per meter cubed times pi 20 meters squared times 17 meters per second cubed. And when you multiply all that together, you get that the output power is 1.05 times 10 to the 6 watts, or 1.05 megawatts. So that's a pretty big machine. Okay, that's the end.